Okay, so we are at a position now uh, where we know all, not all, but most of the different state space relations, which are actually the most popular or the most useful ones. And we have also studied in at a great extent the Jordan canonical form, which is a generalization of the diagonal form. And after all these studying all these different forms and understanding that we can take one form to another, so now comes the question of actually solving the state space relation. So we have a dynamics, x dot equals to ax plus bu, y equals to cx plus du. Now we want to know, want to find out the output y, yt, that is the solution of the system. So in a way the system is always like, um, there is an input going into the system and there is an output coming from the system. So by giving a certain input, what would be my output? That is the question we are trying to solve, and that is the solution. So that output is the solution given a particular input. However, in the state space realization, in the field, in the domain of SPRs, what we have to uh, be uh, be cautious is that the first thing we need to find out is the states of the system, the evolution of the states of the system, because ultimately the output is basically y equals to cx most of the time, because d is mostly 0. So y equals to cx, so we need to know x, right? Even if d is non-zero, u is already known. So what we need is, we need the xt we need to find out, and that we need to find out from the equation x dot equals to ax plus bu. From that equation we need to find out what is xt. So we are basically in this particular lecture, we are basically concerned about the solution of the homogeneous uh, state homogeneous state dynamics. This one, basically we are concerned with the solution of x dot equals to ax plus bu is there, but first we would try to figure out what is the solution of x dot equals to ax, then add the bu to it. So when we see this, we first try to like, we are taking an analogy actually from the scalar homogeneous dynamics. So this is the homogeneous scalar homogeneous dynamics, where x is just a scalar and a is just some coefficient, scalar coefficient, and uh, the solution to this we already know. It is very well known that the solution would come out to be this: e to the power of at x0, x0 being the initial condition. X0 basically is x of 0. So x at t equals to 0 is x0, which is denoted by x subscript 0, and any xt is basically e to the power of at x0. This is well known. Now your e to the power of at can be expanded in a series of in an infinite series of terms like this. So this is the expansion of the exponential e to the power of at. Now looking at this, we extend this idea to vector states. We extend the idea to vector states, and we assume the form of the solution to be what you can see here. In the same manner, we assume the form of the solution. We don't assume these a's to be same. as you can see. So these are some A0 and then some A1, some A2. What we actually have assumed is that this is a sum, this is an infinite series of the terms with powers t to the power of k. So it is a infinite polynomial series, same as an infinite polynomial series we found in case of the scalar dynamics. So why we assume like this, not anything else? You can ask me the question. So in case of the vector also, like what is actually here? We have a set of dynamics x1 dot x2 dot, suppose third order, and some a11 x1 a12 13 a21 a1 a3 x1 x2. Now if your a1 to a13 is 0, if suppose your a1 to a13 is 0, then you see that the first dynamics x1 dot is a11 x1. So it is almost like this, almost it is same as the scalar dynamic. Similarly for x2, if you have a21 and a23 as 0, then again you will get a scalar dynamics, and you know that this system can be actually transformed into the diagonal form. So you basically get a response there which is similar to this. So looking at all these similarities, and we can assume that these solutions of x1 x2 x3 x1 x2 x3, the solutions would also take this sum of infinite series of terms with polynomial degrees of t. So this is what we can assume. Uh, this is a like possible very sort of valid assumption, one can say. So with this assumption we actually go ahead and then we establish what these coefficients a0 a1 a2 etc are. So these are actually vectors, as you can understand. These would be vectors because the t is a scalar, this side you have a vector, so all these coefficients are vector coefficients. And also it is easy to see that your x0, if you put t equals to 0, you will get x0 as a0. So if my solution proposed is this, then from here if you now calculate x dot, you would get this equation. So a0 is a constant, it will not be remaining there, a1, then 2a 2t, then 3a 3t square, like this it will go on. And what is ax? From here only, from here what is ax? Ax is a0 plus a1t plus a2t square, like this. Now your actual system dynamics is x dot equals to ax. So if this ax is a solution, then this side, then this and this would be same. If this is a solution, then this and this would be same. So now we equate the coefficients. So when we equate the coefficients, we see that these are same, and from that we get these relationships, and you see that all these relationships can be actually expressed in terms of A0. Any term now can be expressed in terms of A0. So, I hope you can see this, how this is happening. So, from this equivalence of the coefficients, and what we do additionally, we express all the coefficients in terms of the A0, and remembering that A0 is basically x0, the initial state. So, now we replace all the coefficients A1, A2, etc., and take the A0 out as x0, and what we find inside the bracket is this expression, and this expression, see, look at it, it looks as if it is a matrix exponential. So, if capital A was a scalar, it was very easy to see that this is a exponential term. So, since capital A is a matrix, we call this expression, which looks similar to the exponential series, as the matrix exponential. We denote this entire series as this is a denotation, analogous to the scalar exponential, and we call this the matrix exponential because of the similarity of expression with the scalar exponential. So, if we understand what e to the power of capital AT is, we understand that it is this expression, this infinite series of terms in powers of t with the matrix, with the powers of the matrix as its coefficients, and this 1 by k k factorial a to the power of k as the coefficient of t to the power of k. So, and all these terms would be present. So, if we understand that e to the power of capital AT is basically this, then we can replace this entire term with e to the power of AT, and we write it simply like this. So, now there is a equivalence in expression between the scalar case, which was simply this, and the vector case, which is like this. So, when it was simply a scalar, then A was a small a, it is a scalar, and now it is a matrix. So, A becomes a matrix. So, that is the change only. However, this is not direct, as you can understand, we had to go through some mathematical logic and some like equivalence of terms and all these sort of different um, mathematical proof we have to go through in order to establish that the solution of x dot equals to Ax can be written as this. We have to understand what we mean by e to the power of capital AT, that we need to understand, and we know this is the expression, this is the expression in this box, this is the expression. So, this e to the power of AT that we found out, so is basically it's called the state transition matrix in the continuous linear time invariant case. However, there is a definition, there is a general definition of what is the state transition matrix of a system. So, it is the matrix which, when operated on the so this is the general definition, this is the general definition. So, the matrix function which transitions initial system state x0 to the final state, there should be a 2 here, 2 is missing. The matrix function which transitions initial system state x0 to the final state in a homogeneous dynamical system. is known as the state transition matrix. That is the definition of state transition matrix in general, and in general it is denoted by phi t. In this case, what we see that the state transition matrix is basically e to the power of a t. So, in the case of continuous linear time invariant systems, the STM is same as the matrix exponential e to the power of a t. So, this relationship comes out. The state transition matrix is the matrix exponential. Okay. So, also you see, so that is what we are seeing here. The state x t at any time t is a transition of the initial states x 0 carried out by operation of the time dependent matrix function e to the power of a t on x 0. Thereby it is called the state transition. So, what is happening basically in your state space, if you have a state x 0 from where you start with, this is your starting state, and you will go anywhere, right, because you will move in a trajectory. So, perhaps you are going in like this, trajectory is getting formed. So, all these at all these points you are getting new vectors. So, supposing this is the origin, so getting all these new vectors. So, as we have come to know that there is a relationship between any two vectors through some matrix operation. So, this is M1, this is M2, okay, this is M3. Obviously, this matrix keeps on changing, that is why the distortion is varying and you are getting a trajectory, and this change is sometimes it is M1, sometimes it is M2, sometimes it is M3. So, like this it is changing. So, that variation with time is encoded in this matrix exponential function. So, how this matrix changes with time is given in this matrix exponential. In general, it is some time varying matrix phi. For other systems, it is some phi. You have to find out that phi. For continuous linear time invariant system, we have found out that phi to be the matrix exponential e to the power of a t. Okay. So, when the state transition matrix is the matrix exponential, in that case, so in the case of continuous linear time invariant systems only, in that case several properties emerge for the state transition matrix, and all these are the properties which are very simple to see once you realize that what is phi t. Phi t is nothing but e to the power of a t. So, now you would see, you would immediately realize, and e to the power of a t you have to remember it is what, let us see once this expression. So, e to the power of a t is I plus a or 1 by 2 a t plus a t plus 1 by 2 a square t square plus dot 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 plus like this 1 by k star a k t k plus dot dot dot. So, this is your state transition matrix. So, now you see, now you can easily verify these properties. If you put t equals to 0, then immediately your phi 0 becomes I. If you want to do an inverse, so phi inverse t, if you do an inverse here, as you know by exponential rule, the inverse becomes a minus t, and hence you are getting phi of minus t. So phi inverse t becomes phi of minus t. Phi t1 plus t2. So if you write t1 and plus t2 here, very easily you can see that e to the power of a t1 plus t2 is e to the power of a t1 and e to the power of a t2. So it is phi t1 phi t2, and it will be same as phi t2 phi t. That is a thing. So then phi t to the power of n is basically phi n t. So all this comes by simply looking at this exponential expression, and this also comes directly. Now what is phi dot t? If you take a phi dot t, you will get a plus a plus a plus a t, and then like that. So you differentiate this right hand side, and you will be able to see that you can take a common from that expression, and what remains would be phi t. So phi dot t would be equals to a phi t. So the differentiation of the exponential also happens in the same way as the scalar exponential. So the STM satisfies the homogeneous state equation. This is the important result, that the state transition matrix satisfies the homogeneous state equation, and this result holds true for all the different state transition matrices that we obtain from different systems basically. So here we are looking at continuous LTI, but this is not restricted to continuous LTI. That is what I mean to say. So when we will see other types of system, we will also see that this idea that the STM satisfies the homogeneous state equation, this remains true. Anyway, if you do a phi t, you will immediately see that is same as phi t a. So if you multiply a from this side or that side, it doesn't matter, because in the expression you only have this a terms and the other term is a scalar. Now this will require some proof. It says that if a2 is p inverse a1p, that means there is a similarity transform p which links two systems with state matrices a1 and a2. So from a1 we are going to a2, and hence a2 is p inverse a1p. Then there would be a phi, there would be a state transition matrix in the state space of a1 as well as in the state space of a2. So the phi a2 the phi a1 would be p phi a2 p inverse, or you can also write that phi a2 equals to p inverse phi a1 p. So it is same, like you see a2 equals to p inverse a1p, phi a2 is also p inverse phi a1p. But normally what happens, we are going from a1 to a2, then finding out phi a2 and then coming back to phi a1. Normally this is what we do. That's why phi a1 is written in terms of phi a2. So that's why phi a1 is written in terms of phi a2. And how this is proved? You see, this is very simple proof. a2 is p inverse a1p. So now you know what is e to the power of a2t, this expression basically. This is phi a2t. Now you take any term. Suppose you take the kth term, which is the general term, kth term. So p and what you do, you do this, you do a p a2 to the power of k p inverse, and write it down in this manner. In what manner? Like there are k number of a2s, right? So between any two a2 you put this term p inverse p. So between any two successive a2 you put this term p inverse p. This is basically nothing you are putting I. So you can write this p inverse p in between every successive a2. So k times you will write basically p a2 p inverse, then again p a2 p inverse, then again p a2 p inverse. You will write it k times, and p a2 p inverse is nothing but a1 by this relationship. P a2 p inverse nothing but a1. So you are writing a1 k number of times. So the relationship is this, right? For any term, this is for any term. K can be anything. K can be any integer. So now what you do, this is phi a2 t. Now you put a p in front of this and a p inverse at the back of it. That means at every term you are putting a p and a p inverse. So you are getting a a1 here, you are getting a a1 square here, you are getting a a1k here when you are doing that. So that means by doing this you are basically changing this expression, this entire expression into phi a1. I hope this is clear. So you are basically, when you are doing the p phi a2 p inverse, you are putting a p on this side and a p inverse on this side, and this goes into every term. Each term it goes into. So this p a2 p inverse becomes a1. Similarly p a2 k p inverse becomes a1 to the power of k, and this k can be any number. So all these terms are basically changing into a1, directly changing into a1, and hence we are getting a matrix exponential on of a1. So you are getting phi a1. So this is the proof of the last property, and this is a very useful property because sometimes it is easier to calculate the phi a2 instead of phi a1. So you are in a particular system a1, but you know how phi a2 would look like for a particular system a2. So for a particular system a2, you know what phi a2 would look like. Maybe there is a direct computation of phi a2 for a particular SPR a2. We will see that this when this is useful, because we have to compute the state transition matrices, right? So then what you do, you change from a1 to a2 by applying some transformation, a similarity transformation. Then you directly get this, and then you change back by applying the inverse. So you get phi a1. So you apply the inverse here. So this is how you change. This is how you utilize this particular feature, particular property. Okay. So this is all for the no, there is one more slide. So now with the solution. So if when you have found out the state transition matrix, remember we have found out only theoretically, we don't know how to compute a particular state transition matrix for a particular representation yet. What we did all are theoretical work, but going by this theory, so we will see how to compute. But suppose you have already computed phi t, you have already computed e to the power of at. So when you have computed e to the power of at, what would be the solution of the continuous linear time invariant SPR? So there you can do it in two different ways. In one way, you would have to use the information of e to the power of at. In another way, you don't have to actually. So this one is the inverse Laplace, where what you do, you basically you make a inverse Laplace of the state dynamics considering the initial condition. So you keep your x0. So then your this equation in Laplace domain becomes this, and from here you have a relationship between x and u through the initial condition x0. So x0 also comes into picture. So this is a simple manipulation, and xt is nothing but a Laplace inverse of this. Laplace inverse of this. So you can go via this route to find out what your xt is, and when you found out xt, your yt is simply cxt. There is also the route you can take from directly from time domain. From time domain, what happens basically, your equation is x dot equals to ax plus bu. You change it a bit, x dot minus ax equals to bu, and then you come to this step, you multiply with e to the power of minus at both side, and you suddenly see that what you have in the LHS is nothing but ddt of e to the power of minus at x, and in the right side it is the same. So now you have e to the power of minus at xt as integration of this whole thing. So you do an integration both side. This side you are obtaining this thing, and this side you are obtaining an integration of this term and a k. So, this is a constant of integration, and you can evaluate this k by putting t equals to 0. So, when you put t equals to 0, then you have x0 this side. This term becomes 0 because limit is from 0 to 0, and you have a k. So, k is basically x0 coming out. Then what you have, the solution is that from here, from this equation, you can come to this equation. You are multiplying by e to the power of at both side. So this term vanishes, only xt remains, and in this side you have e to the power of at k, but k is x0, so e to the power of at x0, and integration, you have this term and you have e to the power of at coming in. So e to the power of at minus tau b u tau d tau. This tau is basically a dummy variable because you have to actually take integration from 0 to time t. So tau acts like a dummy time variable. So this is what comes out to be, and your yt is c times this xt. Now you just look into these two equations in left and right. One is in the Laplace domain, another in the time domain. You can very easily understand that this Laplace inverse would eventually give you this equation. So you can go via the route of Laplace inverse, or you can directly come to the time domain equation. That is your choice, and you can actually remember this equation. This is a very standard equation. This is also standard, this is also standard, so both are standard. So you can directly utilize these forms, these equation forms, in order to carry out your further calculations of the or further computation of the solution. So you don't need to come through these steps of proof. If asked, you have to show. If there is a question where you are asked, then you have to show. Otherwise, for a particular numerical example, you don't have to come through these these steps, you can directly utilize these standard equations, the solutions. So this is pretty standard, so you can directly utilize them, and after you find out what is xt, your yt can be very easily computed, simply cx. So here this lecture ends, and in the next lecture we will basically look into the various techniques to compute the state transition matrix. As you can see here, the main thing is the computation of e to the power of at. This is the main thing, because here you have to utilize e to the power at. Here it comes inside the integration. So whatever e to the power at you calculate, you have to replace t with t minus tau, and then put it inside the integration and then integrate. So calculation of e to the power of at is the first. It is the very necessary thing in order to find out the solution of our continuous time and continuous linear time invariant SPR. So this is very important. How to calculate the matrix exponential is what we would look into in the next lecture. So that is all for this particular lecture. Thank you for your attention.